okay, so this is, can't even see the, I think these are sort of the nearest neighbor exchange, and this is the next nearest neighbor exchange. And they see a lot of phases here, which, as far as I know, experiment just hasn't caught up with it. And I don't, I'm not sure what else to say about it. So here's the comment about the spin ice and possible spin glass transition. So one of the most interesting ideas about the spin ice problem is that you can form monopoles, right? Because you can have defects in the 2-in, 2-out tetrahedra, and so you will form monopoles and anti-monopoles, and they are indicated here. And it's work that comes from Sondy and Mersner. But now there are new measurements showing that perhaps this scenario is not the right scenario. That it goes through a good old spin glass transition. Anyway, so this is a very active area. That's all I want to say.
Sorry, question. This phase diagram is for what compound?
It's for the generic spin liquid problem. Yeah. But mostly getting the inspiration from pyrochlores. There are something like 5 candidates now for spin liquid. The Herbert Smithite, which is related to what I'll talk about next, is probably the most promising because you can grow huge crystals and therefore do neutron scattering on them. So that appears to be the one that is gotten most attention, but the others are based on pyrochlores and Kagome systems. Okay, so we are going to look at the Kagome magnet, and the crystals were grown at MIT when Yang Li was still there. Okay, so this is sort of like the Herbert Smithite, except that it's not a spin ice because it orders. You start off with copper, and it forms a beautiful Kagome lattice, right? See here? Kagome lattice is like a Star of David, right? And the nearest neighbor layers are staggered a little bit, but the interesting part is that you can put in a benzene-like ring in between. This was first discovered by Nocera, who at the time at MIT. And the exchange mediated by all these carbon bonds provides a C-axis exchange between the layers and provides the exchange that stabilizes the magnetic phase. So it becomes antiferromagnetic at 2 Kelvin. It has this difficult name, and we all just call it the BDC material. So if you look at the thermal conductivity, it again shows this very interesting change when the system orders at 2 Kelvin. Then you see a big enhancement of the thermal conductivity. And this is very likely the spins, right? Because now you form a spin waves with the rigid spring constant, and therefore it carries a lot of heat. And so we wanted to search for the thermal Hall effect in that system. Now we are back to the initial idea of Nagaosa and Lee, right, where you have a Kagome system, right? So you have triangles where the spins hopefully form a chiral pattern, and therefore there will be a Berry curvature associated with it.
Do you expect to have transport at 0 temperature?
No, these are neutral thermal currents. There are no electrons. What do you mean by expect transport?
Well, does that go down to 0?
Oh yeah. Oh yeah.
Fine.
Yeah, because there are phonons and. Oh, you mean does it dead end at finite value? Probably not. Yeah, because you cannot.
Well, you can't have
you can
0
have
temp.
excitations, that's right.
But
But for us, we can't go to zero temperature because always need to establish a gradient.
Yeah.
It becomes harder and harder to do experiments down here, especially Hall effect. So this gives a broader view. Oh yeah, I should have shown this first. So here's the Kagome Lattice, right? So if the local moments, these are all copper, if they have this chiral pattern, right, it make a solid angle, and if all of them had the same sign of the rotation, then you would expect a very large chiral current. So this was the original motivating idea from Nagaosa and Lee's paper. So the thermal conductivity, the phonons die very rapidly, and then we're down here. And this little tiny anomaly, which I show expanded here, signals the dominance of spin excitations, we believe. And you can plot it as the kappa divided by T and show it more clearly. So there's this mixture of spin and phonon excitations here, but over here is probably predominantly spins. But now it's ordered, so so theorists can now work more closely with us because they can really attack the problem using all these powerful numerical techniques. Okay, so first I show again kappa XX versus field at various temperatures, and there's not much going on until you get to like 5 Kelvin, and then close to the magnetic transition, you see a very rich pattern of behavior, right? So I zoom in here, and you see a very rapid drop in the thermal conductivity, and then there's nothing left, right? So it's very tempting to identify the flat background here with phonons, and therefore if you want to get a pure spin excitation, we simply subtract off the background. And so here you're seeing the effect of magnetic field on the magnon branches, and how the changes then affect the thermal transport. But it's the thermal Hall effect that we're looking for. Let's see what this plot shows. This plot shows the same thing. It's the previous data after we have removed the background. So now this we believe is purely due to the spin. So again, it's a very rich pattern of behavior extending down to a half a Kelvin. So you see a very large Hall effect, as I'll show you in the next slide. But here I'm comparing the kappa XX from the spins alone. That's what a superscript indicates. And you see it has a decrease with magnetic field that matches the Hall signal, to be shown in the next slide. So the Hall signal must come from spins, right? Because phonons simply don't have this Berry curvature effect, at least to such a large value. And the fact that the two of them track in magnetic field gives us added confidence that we are indeed, that this is correct, that this is all caused by spins.
Phuan?
Yeah.
Would you see something like that in the peak capacity as well, or
In the amount of spin excitation,
yeah.
how could you tell? I mean, yeah, you would see something, I'm sure. But how could you tell whether? There's some ordering of the spins. Yeah, you could see that. Yeah, but we're looking for the Hall effect. Actually, heat capacity was done. I forgot what it looks like. Yeah, I should look it up. I think it's been done. So here's the Hall effect, and it's huge. I mean, it's a very busy series of curves. It does all kinds of things as you go through the transition. So there are two samples shown here, sample 2 and sample 3, right? So maybe I'll just forget about sample 2 and just talk about sample 3. So here are the, quote, high temperature curves. When you are starting at 8 Kelvin, all you see is this sort of linear field dependence. Then as you cool down, it picks up a lot of action, right? It starts to have a strong curvature. And when you get to 2 Kelvin, now we're just above the magnetic transition, then there's this whopping big dispersion-like curve. Now we go below, so this big up and down curve now looks like this, right? And it continues to evolve and has this very sharp spike But anyway, so this is obviously there's a lot of things going on, but what it's telling you is that yes, there is a huge thermal Hall effect that kicks in below magnetic ordering associated with the magnons, and resulting from the Berry curvature engendered by the chirality. Right? Now, this show you the same thing. Oh, am I out of time? Okay, this will be the last slide. So Lee, Han, and Lee, this is Patrick's group with some visitor from South Korea, actually went ahead and did the calculation using now the correct approach of Murakami in the TJ model. And to handle the, so they have added Jeloshinsky, Moria term, and the Zeeman energy as well. So they made, to calculate the thermal conductivity, they need a model for the spin ordering. So they have used either the Holstein-Primakov model or the Schwinger model. And this will become apparent in the next slide. First of all, the band structure can be done for the spin waves, right? And you see 3 bands, the lowest lying bands. And in the magnetic field, the bands will split and move. Now, the reason for walking you through all this is because this will lead to changes in sign of the Berry curvature. And as you occupy, unfortunately, magnons are bosons, so it's not a sharp distribution. You know, even at the lowest temperature, you have a broad distribution that allows you to occupy high line bands. That's an unfortunate part of this, of the excitation. But nonetheless, you should be able to see changes of sign, right? Because these bands have different Chern numbers, and they force the Hall effect to change sign when you cool down. And you see the calculation do that, right? So these are calculations, and they sort of imitate what the experiment is saying, especially the curve at 2 Kelvin. So it goes up, comes down, the Hall effect, as it does here, right? It even changes sign. But the details are, of course, very specific to the model that they apply. Interestingly, the Schwinger model, which is what this is, Schwinger boson, does poorly compared to the Holstein-Primakov model. And that, of course, is something that needs to be worked out. But here now we're beginning to be able to compare actual measurements of this chiral current and make comparisons with a rather complicated calculation based on these spin models. And I think that this is going in a good way. So to summarize, do you want me to talk about this? I'm sort of running out of time. But anyway, this is the relation of thermal conductivity to gravity effects. It turns out that many of these authors have pointed out that what's called the near Minkowski regime, where distortion of space-time is weak, you can actually couch all the gravity equations and pull out what's called the gravito-electric field and the gravito-magnetic field. And the biggest consequence of this is the frame dragging experiment that Fairbanks and company. You fly a satellite, and you see that the gyroscope gets dragged by the rotation of this mass. So think of the mass rotating around as the Amperian current in Maxwell physics. And this Amperian current then gives rise to a magnetic field, which in this case is the gravito-magnetic field. That magnetic field then acts on the mass of the gyroscope, of course acts on as a torque, and then the gyroscope responds by precessing. So this has been measured, and this is very similar. So the same kind of ideas get translated using Luttinger's approach to calculate kappa xy. So there's a lot of interesting predictions having to do with what's called the central charge, made by many people, starting with Kane and Fisher, that seem pertinent to the quantum Hall effect as well as the topological insulators. So this is the growth area that probably will happen in the next few years. Okay, so let me just put up a summary slide and stop there. Thank you.
For your Hall current experiment, can you take your sample, rotate it, and then measure the same day?
No. You need to spin it at extremely high. But that's not exactly what they're talking about. It's yeah, it's not that you spin the sample to get a Hall thing.
But if you had done that, in that case, would you expect
No,
that
you wouldn't. No, no. These are all painfully slow experiments in cryogenic temperatures at high magnetic field. You can't spin them. Yeah.
Can you go back to the slide that has the organic mediated Kagome Lattice? So yeah, so what was the point of having the organic?
It's to provide interlayer exchange.
So you want to have more. You want to have more
C-axis,
vertical,
yeah,
okay,
moderate, yeah.
exchange. So
It's not that you want to. That's the way it grew. You know, I think Yang Li brought the attention of Dan Sarah that it sure would be nice to have a system that had Kagome Lattice.
right.
And was like, yeah, I know one.
So
And that's what he came up with.
So say in attempts of growing a new Kagome structured material, we want to have, say, something that another mediator that would increase that interaction.
No, that would decrease it because if you want to spin
You want
liquid.
to interact, you
So
want
the Herbert-Smithite is like that.
Okay.
Herbert-Smithite is Kagome, and then with some zinc system here, but somehow it doesn't order.
Okay. So they're all like insulated from
Yeah.
each other. Okay. Thank you.
Other questions? Okay, I guess we'll have a break, and then I'll talk about the other material.